Have you ever stopped to wonder what's really going on inside your phone or your laptop? It feels like magic, but it's not. It's an incredible, hidden world of microscopic engineering. Today, we're going to pull back the curtain on the secret ingredient that makes all of our modern tech tick. Let's dive in.
So what's the real force behind our digital lives? I mean, what is it that makes everything from streaming a movie to sending a text even possible? You might think it's just electricity, but that's only half the story.
You see, the real secret, the absolute game changer, isn't just having electricity, it's the ability to control it. We're talking about the power to switch it on and off, to guide it with pinpoint precision, billions upon billions of times every single second. And that kind of control, well, it's only possible because of one very, very special kind of material.
And that brings us to what I like to call the Goldilocks material. You know the story, right? We need something that's not too conductive and not too much of an insulator. We need something that's just right.
And that magical material is, you guessed it, a semiconductor. It really is the perfect middle ground. Think about copper. It lets electricity flow like a raging river. Then think about rubber, which stops that flow dead in its tracks. Semiconductors sit right in that sweet spot in between.
Now, the most famous one by far is silicon. You've heard of Silicon Valley, right? Well, this is the stuff. It's the same element found in sand, which is pretty wild to think about. But there are others too, like germanium or gallium arsenide, that are used for more specialized things, like superfast circuits or even lasers.
Okay, this table really lays out that Goldilocks principle perfectly. Look at conductors. Electricity just zips right through. Insulators, total roadblock. But check out semiconductors, right there in the middle. And here's the really cool part. Notice how their conductivity actually increases with temperature? That's a huge clue that we can manipulate them, that we can control them.
So what's the deal? Why do they behave this way? Well, the secret lies in something called the energy gap. Now I know, that sounds like something straight out of quantum physics, and it is. But the core idea is actually pretty straightforward.
So imagine electrons need to jump over a hurdle to get into the conduction lane and create a current. For conductors, there's no hurdle at all. They're already in the lane, ready to go. For insulators, that hurdle is like a giant canyon. There's just no way to cross it. But for semiconductors, it's just a small, manageable hurdle. Give those electrons a little nudge of energy, and boom, they can make the jump. That's the key to their controllability.
But here's the thing. A pure semiconductor on its own is, well, it's kind of boring. It's not useful enough for what we need. To really unlock its potential, engineers figured out a way to essentially hack the system. And this incredible trick is called doping. Think of a pure or intrinsic semiconductor like a blank canvas. It has potential, but it can't do much by itself. But by intentionally adding just the right impurities, we create what's called an extrinsic semiconductor, and we can crank its conductivity way, way up. So what is doping? It's literally just adding a tiny, tiny amount of a specific impurity into the semiconductor's crystal structure. It's like adding a pinch of salt to a giant recipe, a very small change that completely transforms the final result. This simple hack is the absolute key to everything that follows.
Now, this doping process doesn't just create one new type of material, it actually creates two very distinct flavors. So let's meet the two key players in this whole story, the positive team and the negative team. The two types we can create are N-type and P-type. N-type, which stands for negative, gets doped in a way that gives it an excess of electrons. And P-type, for positive, is the opposite. It's created with a deficit of electrons, which we call holes. This simple yin and yang difference is what makes the whole thing work.
Okay, so how do we make an N-type semiconductor? We take our silicon, which has 4 outer electrons for bonding, and we add a donor impurity, like arsenic, which has 5. When they bond together, what happens? 4 of arsenic's electrons pair up with silicon, but there's 1 left over. And that extra electron is now free to roam around and conduct electricity.
Now to make a P-type, we do the exact opposite. We add an acceptor impurity, like boron, which only has 3 outer electrons. When it tries to bond with silicon, which is looking for 4 partners, there's a missing spot, an empty spot where an electron should be. And we call this empty spot a hole.
So a hole isn't a real particle, right? It's just the absence of one. The best way to think about it is like an empty space in a packed parking lot. When a car moves forward to fill that empty spot, it leaves its old spot vacant. It looks like the empty space just moved backwards. It's the same idea here. An electron jumps into a hole, leaving a new hole behind, making it seem like a positive charge is moving through the material.
All right, so let's recap. We've cleverly created 2 opposing materials. One with a bunch of extra electrons, and another with a bunch of electron-sized empty spots. So what's the next logical step for any engineer? What happens when we stick them together? Well, what you get is maybe the single most important invention in modern history, the ultimate electronic switch.
This meeting point, this boundary where the P-type material and the N-type material come together, is called a P-N junction. And this simple interface, this tiny little line, that's where all the magic really happens.
Seriously, the P-N junction is the fundamental building block of almost everything. It's the Lego brick that we use to build diodes, transistors, and the insanely complex integrated circuits that power our entire world. It all comes back to this one simple, repeatable unit.
So what does it actually do? In a nutshell, a P-N junction acts like a one-way gate for electricity. It's like an electronic check valve. It lets current flow through easily in one direction, but if you try to send it the other way, it slams the gate shut.
And we can control this gate just by applying a voltage. If we apply it one way, called forward bias, the gate swings open and current flows. If we flip the voltage, called reverse bias, the gate slams shut. On, off. Flow, no flow. This is it. This is the physical representation of a 1 and a 0, the fundamental language of all computers. And from this one simple on-off switch, you get pretty much every electronic component you can imagine. Diodes that direct current, transistors that act as switches or amplifiers, LEDs that give off light, even solar cells that convert light into electricity. They all start with the humble P-N junction.
So let's bring this all back home. The processor in the very device you're watching this on right now contains billions, literally billions, of these microscopic P-N junction switches, and they are flipping on and off at unbelievable speeds to perform every single calculation. Every pixel on your screen, every bit of audio you hear, is the result of these tiny gates opening and closing.
For the past 50 years, all of technological progress has basically been about making this one tiny switch smaller, faster, and cheaper. But we're starting to hit the real physical limits of silicon. So it makes you wonder, if this P-N junction is the fundamental atom of modern computing, what's going to be the molecule of tomorrow's technology?